Hi, I'm Leonardo Roland. This is the first video of the second half of week 1 of module ST342, Mathematics of Random Events. You will see that we are getting more theoretical, and there will be many exercises which, let's say, are micro gaps left in the theory for you to fill so that you will learn actively and not just receive information bundled and conveyed to you. This lecture has two parts. The first is about sigma algebra, and it's covered in section 2.1.1 of the lecture notes. And the second part will be about algebras, and it's covered in section 2.1.4 of the lecture notes. It is strongly recommended that you read these subsections before you watch the video. So we start with sigma algebras, and here's the definition. What is a sigma algebra? So sigma algebra is a collection of subsets of a sample space omega. Sample space omega is any set which is not empty. And so it is a collection of subsets of omega which has some structure. And if it does have that structure, it will be called sigma algebra. In this module, it is also called sigma field in some books and articles. And in order to be called a sigma algebra, this collection of sets must have some structure. And what structure is it? Well, first, the entire sample space omega is one set that belongs to this collection. Second, for every set in the collection, its complement, so what is this? This is the set of points which belong to capital omega but do not belong to A. So the complement of A must be in the collection. And for any countable collection of sets in this family, the union of that collection, so this will be again a subset of omega, it must be in the collection. So if it satisfies these three properties, we'll call this collection a sigma algebra. Then the pair omega, together with this family of subsets of omega that has this structure, this pair is called a measurable space. So it's a measurable space, which means it's amenable for us to do measure theory on this set. So sets in this family, they're called F-measurable sets, which means they're measurable only in the sense that they belong to the family. So this is just semantics here. And we simply call them also just measurable sets if it's clear from the context that the collection under consideration is that F. So from these three properties, we have another two properties which are very easy to prove, and you can prove them as exercise if you want. That the empty set is also a member of this family, and for any countable collection of members of this family, their intersection will also be in the family. Here are some examples. The first example is the set of all subsets of omega, okay, which we denote by P of omega, and the set of all subsets of omega, it is a sigma algebra on omega. Second example, if we have a given sample space omega and we take only the family or the collection of subsets which only has the empty set and omega itself, then it is a sigma algebra on omega, and it's called the trivial sigma algebra. And here's a proposition, and the proof is an exercise for you. That is, if we have two sigma algebras on the same, so in a given sample space omega, it is the same sample space, and we take the intersection of these two sigma algebras. So the intersection means it will be this family of sets that belong to both of these sigma algebras. Okay? Then we call it like this. This family, it is also a sigma algebra of omega. And I think it's a good exercise. You can stop the video now and try to prove it before moving forward. Now, another property is if we have a function f that maps one sample space to another sample space, and we have a sigma algebra in the second sample space, the one here on the right-hand side, if this f2 is a family of subsets which is a sigma algebra on that sample space, then if we take the pre-image of all elements of the sigma algebra, so here for all elements of the sigma algebra f2, which is a sigma algebra, again, of subsets of omega 2, if we take all the pre-images of all these sets, this gives us a family of subsets now of omega 1. We may wonder whether this family is a sigma algebra on omega 1. And the proposition says, yes, it is a sigma algebra on omega 1. The proof of this proposition is also an exercise for you. And here's a diagram that helps us visualize what is happening. We have a sample space, which is just a non-empty set, a function that maps the points of this space onto points of a second sample space that we call omega 2. So if we have a function that takes points of omega 1 into points of omega 2, and we have a sigma algebra on omega 2, then we can use the same function to define a sigma algebra on omega 1. So the function goes from omega 1 down to omega 2, but we can pull back a function, a sigma algebra on omega 2 to a sigma algebra on omega 1.